Okay, so this morning's section, lots of stuff went wrong. So I hope everything seems to be fixed now. I had to do a complete OS upgrade on both my machines here to get everything working again, and hopefully it doesn't die out again. But in any case, what we're going to do is we're going to continue working on algorithms and algorithm analysis. In particular, we're going to introduce the formal definition of big O and asymptotics. We'll do a couple of examples. We'll talk about different interpretations and proof techniques for proving big O analysis. Remember that the entire motivation is that we want to characterize an algorithm's performance or complexity with respect to its input size. Right? And in step 4 that we were developing last time, we came up with, we identified the step 1 through 4. We identified the input size, n, and so we fixed a variable that characterized that input size. Then we chose an elementary operation to analyze the algorithm with respect to, and then we analyzed it and and counted up how many times do we execute that elementary operation with respect to n. Right? And we came up with a couple of examples like selection sort, quick sort, eventually quick sort, and a couple of others using some different techniques that we'll introduce here in a moment. But otherwise, you come up with this function, this t sub n function, right? We're just calling it t sub n because it's time, right? Time. This is going to characterize the number of elementary operations executed with respect to the input size n, right? And so now what we want to know how that function grows with respect to the input, right? So we're more interested in how the algorithm will perform with larger and larger inputs. In other words, i.e., as n tends towards infinity. Right? As n grows and grows and grows. We don't care about small input sizes because if you remember when we started this whole thing, I gave you a demonstration of traversing over a linked list, right? And the painter that refused to pick up their paint can with them and always walked back and forth and back and forth. For small lists, say lists of size 10 or 20 or 100 or something, right? The difference between a linked list and the array-based list was nothing. It wasn't even noticeable by human standards. It's only as we got up to, say, millions of elements or billions of elements that the contrast becomes absolutely clear, right? 18 hours for 10 million versus less than 1 second, right? 100 million, 10 seconds versus 74 days. 1 billion, 20 years versus 2 minutes, right? It's only as the input sizes get really big that the difference starts to matter. So we only want to know how it performs as n tends towards infinity, right? Ultimately, we want a tool that will ignore lower order terms, right? And only focus on the most significant term that contributes to the growth of the function. And 2, we will want to ignore constants, right? Because you can always upgrade your hardware, right? Who cares if the constant is 0.001 or 100? If you take it and move it to a different machine where it's twice as fast, then it will be half as big, right? All right. We will be limited. We will be limited by my battery size, which will hopefully last the hour. We'll see how long this goes. Yep, we're at 88%, so we should be good. Okay. Anyway, the tool that we're going to use for this is big O analysis. And as I hinted at last time, big O is just O. It's Omicron technically, but the Greek letter Omicron is the same as O, so there is really no difference. Let's go ahead and get into it with the definition. Right? So here's the definition. Let f of n and g of n be functions, right? And in term, this is the big O actually predates modern computer science by hundreds of years. We adopted this tool. Actually, I forget who it was. It's given credit for adopting this, but it was adopted as a tool. It was a calculus tool. It's an analysis tool, and it was adopted by computer science to characterize algorithms. So you can talk about these things as functions generally, but in our context, suppose that these functions characterize two algorithms, right? A and B. And so we are trying to set up a relative performance measure between these two algorithms, right? F is capturing the efficiency of A, and G is capturing the efficiency of B. And now we're going to say that one is better than the other, right? We say that f of n is big O of G of n, right? And write that f of n is equal to big O of G of n. That's technically not correct. Well, I'll talk about that here in a minute, but that's the notation that we're going to use. If there exists a positive constant c and an integer n naught such that f of n is less than or equal to c g sub n for all n greater than or equal to n naught. There's the formal definition. Now what we're going to do is we're going to come up with a couple of interpretations of this thing, okay? The first interpretation is, of course, the one that it's meant to be. Big O characterizes the growth rate, or order of growth of a function, or the relative order growth rate of two functions, right? It basically states that G sub n's growth rate is at least, and let me emphasize that, at least as big as f of n. Right? With respect to the perception of G, with respect to f of n, right? F of n, it says that it is bounded above by G of n. Right? F of n's growth rate, I should say. Growth rate. Right? So why do I emphasize at least and bounded above? It's because of this less than or equal to here. Right? It is not necessarily strictly less than. Of course, you can talk about that, but it's not a loose bound. Right? We're just saying that this function grows at least as big as this function. They could be the same. Right? In fact, here's some examples. Right? It's not a loose, it is not a strict, I should say, strict relative comparison, right? For example, n, let's say 3n plus 5, right? That is a linear function, right? We would say that that is big O of n. What else is true, though? 3n plus 5 is also big O of n squared. Right? That's true. It's also big O of n log n, right? If you have another term here, another logarithmic term, right? You can get bigger and bigger and bigger if you want to. It is order n cubed. You can go up to a exponential value here, right? Every single one of those statements is true. That's because big O is it's not a strict bound. It is not equal to, it is less than or equal to. That's the definition, right? But what is false, right? The following are not true. Right? So, for example, is it true that, say, 3n squared plus 5n is big O of n? That is definitely not true. Right? It doesn't work the other way around. The thing on the right-hand side is a bound on the thing on the left-hand side. Okay? We also don't write, we do not write, say order n is equal to 3n plus 5. Right? And that's because this is of the abuse of notation. Right? So take note of the notation. Right? That strictly speaking, the equality is not correct. Right? The thing on the left-hand side, LHS, left-hand side, is a function. Right? The thing on the right-hand side is not a function. It is a class of functions. Right? Functions. There we go. It is a set of functions. And so the correct, technically correct notation is going to be that f of n is in order g of n. There we go. So if you've had set theory before, you'll have recognized this this notation, right? The backwards epsilon basically is that the thing on the left-hand side is a member of the set on the right-hand side, and it is a class of functions, a set of functions. Don't worry about it for this course. We'll go ahead and abuse the notation and say equals, but you do not write it the other way around. Right? You read it left to right. Okay. The following are not true. We don't write that. Also, another example here, say 2 to the n is order, n, right? That is not correct, right? You can't bound an exponential function with a linear function from above, okay? All right, so let's look at the interpretation of these things, okay? I'm going to go ahead and go with these two functions as examples. So here's another example. What if I've got function f of n is equal to 175 n squared plus 50n, okay? And g sub n is going to be, say, n cubed. We'll keep it simple, right? First of all, which one of those functions is bigger? What does our intuition tell us? Intuitively, we know that f of n is a quadratic, right? And so it's going to be order g of n, which is what kind of function is g of n? Cubic, right? Right here, this guy right here, okay? So our intuition is telling us that this quadratic function is big O of this cubic function. What does that look like with respect to, say, the graph of these things? For that, I'm going to go ahead and open up Wolfram Alpha here, all right? And let's plot those things. I'm only going to plot it from 0 up to 200. I'm not going to plot negative values because you can't have negative input values. Right? Now, when we look at this plot here, I'm going to have to zoom in manually because zooming in is actually a paid feature of Mathematica. And Mathematica is a product that Wolfram Alpha is based on. So look at this graph and tell me what the interpretation of this graph is. The x-axis is the input size. Right? The y-axis is the time that it's going to take you to execute those algorithms that are characterized by these two functions. Now, if you only focus on, say, input sizes from 0 up to 150, which one of those graphs is better? Again, if you only focus from 0 up to 150, and let me go ahead and do that, actually. I'll go ahead and go, and nope, only go ahead and look at 150. Right? We're not even going to look at the entire graph here. Which one of those is better? Now remember, the y-axis is time or resources. So more resources is better or less resources? Remember, you're paying for the resources. So fewer resources is better, right? Less time, less memory, less electricity to run your Bitcoin farming operation, right? And so from this, we see, well, which one's better? The red one, which is n cubed. That would only give us a misimpression on small input values. When we zoom back out and see from 0 up to 200, we see that there's this crossover point right here, right? That as you get larger and larger inputs, at some point, this is that n naught, this function will always be greater than the blue function right here, right? And that n cubed now dominates and is larger. And so that is why we say that this f of n, the blue one, is big O of g of n, the red one. Right? After some point, they will never meet again, and this one will always be greater. Right? So in other words, the one on the bottom is bounded above by this function here. Blue is going to be bounded above forever, off to infinity, by red. 2000 might be too much. There we go. There. right? If we map it all the way out here, we will see that this function will never come down again, and it will always be bounding the other function from above. Okay? That's the graphical interpretation of that. Okay? So, how do we go about proving these things? Okay? Proofs. Right? So, given two functions, f and g, we want to show one or the other, right? Now, usually the first step is you apply your intuition. If this one is quadratic and this one is cubic, well, clearly this one's larger, so we'll go ahead and put it over here, right? If this one is exponential and this one is linear, obviously we'll put this one over here because it's bigger, right? So you come up with an intuition, and then now you need to prove that intuition. I'm going to give you two techniques, and they're both algebraic techniques. And if we've got some calculus, then we can go ahead and look at those as well. But the first approach is to find what's called a crossover point. That's what this visualization was here. Let me go ahead and go back to 200. This is a crossover point. After that point, this red function will always be on top. If you can find this point, then you've found your n naught in the original definition, right? Remember that we say that f of n is big O of g of n if there exists these constants c and n naught such that this inequality holds. That's the definition. Approach A will be to find that crossover point where that one function becomes larger than the other function for all values greater than that crossover point. In other words, algebraically, what you're doing is you need to find two numbers, c and n naught. Fix one of them and then find the other one. In this case, we're going to fix c to be 1, and then we're going to find n naught, after which those functions never meet again. Approach B will be just the opposite. Fix n naught to be 0, and then we'll find c. Right? Let's go ahead and go with approach A on this particular example first. For that, I'm going to thankfully be thankful here that my iPad is now working. Yay. All right, good. All right. So let's go. We want to show that, what are my functions again? What were they? 175 n squared plus 50n is less than or equal to some c times n cubed for all, I'll write it, for all n greater than or equal to n naught. Okay? Now approach A here, technique A, will be to simply fix c to be 1. Right? What happens to this inequality right here when I fix c to be 1? It goes away. Right? So in other words, we want to show that 175 n squared plus 50n is less than or equal to, again, c is going to be 1, so it goes away, for all n greater than or equal to n naught. This is what I need to find now. Right? I need to find a value n naught such that that inequality holds. Okay? Well, when does that equality hold? So what I'm going to do is I'm going to go ahead and transform this into an equality. Okay? Now, for what values of n is that true? Remember, we're trying to find that crossover point here. How do you know when two functions meet, when they intersect? You set them equal to each other and you solve for x, or in this case n, because I've named it n. Okay? I've set them equal to each other. Now all I need to do is find n. Help me out, algebraists. This is algebra. This is just arithmetic with variables, which is what algebra is. Right? Okay. Well, first let's get it clean. All right. Let's go ahead and take everything onto one side. N cubed minus 175 n squared plus 50n is equal to 0. And now it will become abundantly clear what I'm actually trying to find. Roots, right? I'm trying to find the roots of a polynomial in this case. You already observed that what can you do immediately? Factor out an n, right? So what's one root? 0. If we look at this this graph here, they are intersecting at 0, right? What's another value at which they're intersecting? Well, once I've factored out that n, what am I left with? N squared minus 175n plus 50 is equal to 0. Now what tool do I bring to bear to solve for n? The quadratic equation, right? What is that going to be? Negative b, which is negative 175, negative minus 175, so 175 plus minus square root of b squared, 175 squared minus 4ac, so that's going to be what? 4 times 50 is 200, all over 2a, a is 1. Pull out your calculators and tell me what that is. Or, let's go ahead and go with Wolfram alpha.
What does Wolfram alpha not do?
It doesn't do a lot of things if you don't pay for it. Like I can't enlarge this. If I wanted to enlarge this, it says, okay, you can start paying us monthly fees here, right? Anyway, there are the roots. Okay, and let me zoom in on that too because it's kind of small. Hey, there's that root that we were talking about, 0. Here's another root. So one of those roots is negative 0.28. Is that relevant? Why not? Because input sizes cannot be negative, right? All right, and then the last root is going to be, what was it, Wolfram alpha? This thing right here, 175.28. Now, that's the actual crossover point of these two values right here. Have you ever heard of an input size of 175.28? No. So what's the next value for which these functions will no longer ever meet again? 176, right? So by setting up an inequality and finding roots, right? You take the largest value of n, the largest root value, and then the inequality will hold for n not being the largest value, and c being 1. Right? Great. Example 2. N to the 50 plus 3n to the 49 plus 7n to the 48 plus 17n to the 47th ... If I gave you a degree 50 polynomial, how excited would you be to find all those roots? Ecstatic, huh? Well, you could throw it into Wolfram alpha, but then you'd still have to type it all out, and you'd still have to make sure that your typing was correct, et cetera, et cetera, et cetera. Right? This example worked. Why? Because it was artificial. I made sure that there was one easy route to get rid of it and to go down to a quadratic equation so that you could bring this very easy tool to bear. Right? Not all of them are going to be like that, which is why I recommend, between these two techniques, I would recommend that you take approach B. What we're going to do is we're going to fix n not to be 0, and then we're going to find a c such that that inequality is satisfied. Now, graphically, what does that mean? Okay. So what we're going to do is we're going to, we want to, here, let me go back over to my notes here, right? And we want to show, right, we're going to fix n not to be 0. And we want to show that f of n is less than or equal to c g of n for some c. Right? And for our particular example, it was 175n squared plus, what was it, 50n, is less than or equal to some c that we're going to have to come in and find of n cubed. Okay? Now, what does that look like, right? Graphically? What I want to do is I want to take this red one and I want to multiply it by some value c so that it gets bigger and bigger and bigger. let me go ahead and try it with, say, C. Here's my C, C times. What if C were, say, 1? Then you would have exactly what we had before, right? What if I increased C to 2? What does that do? That changes the crossover point. Why? Because it made it a little bit steeper, right? Little bit steeper, little bit steeper. I'm going to make it steep enough that this crossover point moves from way over here. It already jumped all the way over here. I'm going to move it so that it jumps over here. Maybe 3 times as big. Right? And you're not going to be able to see it here, but if we zoom in on it, say only to 20, you'll see that it's still out there. Right? Maybe not. Maybe 50? Nope, a little more. 60? Okay, there we go. There's the crossover point, right? What if I went up to, say, 4 times as big, and then I'll zoom in on 50? There, I moved it over, right? It's now somewhere between 40 and 50. What if I increased it again to 5? Remember, it was between 40 and 50. Now it's between 30 and 40, right? I just have to keep doing this until I find a C that works. Now, this is what it looks like graphically, right? If I went up to 50, I don't know. Looks almost like it works. It looks like it's between 0 and 10 now. Zoom in. Nope, it's still not there. It's between 2 and 4 now, right? So let's kick it up another notch. Let's just go jump up to 100, right? And maybe now it's less than 2, right? That's visually what I'm doing. Now, how do you actually achieve this algebraically? Right? What we're going to do is we're going to take, we're going to take this thing on the left-hand side, and we're going to make it look like the thing on the right-hand side. So let me go ahead and start out with the left-hand side. 175n squared plus 50n. Right? We want to show that that is less than some c n cubed. Okay? So I need to simply make this bigger. What's one way that I can make this bigger? 175n squared. Well, I could make it bigger by saying that it's 100n, right? That doesn't help me in collapsing these two things down to one term, because on the left-hand side, I've got 2 terms. On the right-hand side, I've got 1 term. I want to collapse this down to 1 term. Oh, okay. Multiply the second one by n, and giving me 50n squared. Right? That's true for all n greater than or equal to 0, right? Now, if n were negative and I multiplied by a negative, I wouldn't necessarily be in the same boat, but that's okay in this case. Well, that's equal to, now I can collapse that down to 1, right? 225 n squared. Right? Does it look like the left-hand side yet? Not yet, but we can do one more thing. Your exact same trick as before, right? And this is 225 n cubed. Just multiply by n again. And again, for all n greater than or equal to 0. Now, does that look like the right-hand side? Yeah. For n naught being 0 and c being 225, then the inequality holds. And you've proven that f of n is big O of g of n. Way easier than the first technique of finding roots and crossover points and stuff like that, right? All you need to do is start out with the left-hand side, f, and just make it bigger and bigger and bigger until it looks like g of n. Right? And then you've got your c. There are an infinite number of n naught and c combinations, right? This would be true if I kicked it up another notch and went c is 500, right? 1,000, right? Once you've gotten down to 0, it doesn't really matter, right? Let's go ahead and go up to 225, right? Now that crossover point is definitely at 0, right? Because I've moved the other root maybe to the other side, or I've moved it to match it for 0, right? Well, the same thing happens if you kick it up to 500. It really doesn't matter. It's not a tight inequality. You don't need the smallest possible c. You just need a C that works. Or un-C or whatever. Yeah, AC. Yeah. Okay. All right. Questions on those two proof techniques? Otherwise, here's the third one, right? This is the one that will require calculus, right? If you set up a limit, if you set up a limit as n tends towards infinity of these two functions, of the ratio of these two functions, one of three things is going to happen, okay? What happens when the numerator function, the function on the top, is growing much, much quicker than the function on the bottom? It will diverge off to infinity, right? And this means that the one on the top is growing much, much larger. That means that you've got g sub n is big O of f of n. Okay. What if the one on the bottom is growing much, much quicker than the one on the top? It will converge to 0, which means that f of n is big O of g of n. What's the other possibility? That they cancel each other out, right? And that it converges to some constant c greater than 0. That's not the same c, by the way, right? In this case, you've got f of n. Oh, sorry. F of n is big O of g of n, and g of n is big O of f of n. Because they have the same growth rate. Because their growth rates cancel each other out and you converge down to some constant eventually. Right? We call this thing right here big theta. F of n is big theta of g of n. It's an asymptotic equivalence, basically. Because it's, this one bounds it above, and it also bounds it below by some constant. We won't get into the formal definition of that. That's 235 material. Okay? But there's your limit method. What would it look like if we set up a limit for our two functions that we just played around with? What was it? 175 n squared plus 50n all over n cubed. Right? You can go ahead and split this up into two sums. Right? And then the limit of sums is equal to the sum of limits, as long as they converge. They will. N tends towards infinity of 175 n squared over n cubed plus the limit as n tends towards infinity of 50n squared, or sorry, 50n over n cubed. Tell me about that first limit right there. Well, the n squared cancels with the cube, and so what am I left with? I'll pull the 175 out front so that we're in something I call obvious land. What happens to the limit of 1 over n as n tends towards infinity? 0. Right? What about the second one? N cancels with this, and you have limit as n tends towards infinity of 50 out front now. And then what do you have? 1 over n squared. That's even more obvious land. Why? Because it's growing even quicker on the denominator, and it's converging to 0 even quicker. So, plus 0. In other words, 0 plus 0 is 0. And which case do we have here? F of n is big O of g of n, which is the same conclusion as our two previous examples, our two previous techniques. Okay? All right. Do I have more examples? I thought I'd pull out the textbook and see if there are examples ready-made for us here. Nah. I've only got limit techniques here. That's all right. That's good enough for now. Okay. So, those are two proof techniques. Now let's go back to what we left off with last time with quicksort. And what about asymptotics on recursive algorithms? Right? So recall quicksort. it had we basically did we set up a function c sub n to be equal to the number of comparisons by quicksort on an array of size n. Right? There we go. And then we came up with an expression for c sub n, right? C sub n was equal to 2 c sub n divided by 2 plus n minus 1. Remind me where those came from, right? Where was n minus 1 comparisons? That was coming from the partition method. Comparisons to partition the array into two roughly equal subarrays. I say roughly equal because you could get into the worst case scenario is where you end up partitioning everything to one side and now you're just doing selection sort, right? We're going to assume that it's on average case or the best case scenario where it ends up as a roughly even split. Right? Then we had 2 recursive calls to each subarray, right? Each requiring c sub n divided by 2 comparisons. Now, where did we get that? C sub n divided by 2 comparisons. That was the very definition of c sub n right here. The number of comparisons by quicksort on an array of size n. If you cut it in half, that array is going to be size n divided by 2. So how many comparisons does quicksort make on an array of size n divided by 2? C sub n divided by 2. 2 recursive calls here because we went on the left side and the right side. The left side and the right side. Okay? So we came up with this expression right here. Now, if you were to solve this, you'd have to probably unroll it. Right? What would that look like? C sub n is equal to 2 c sub n divided by 2 plus n minus 1. Take this and plug it back in over here. And what do you get? 2 times, when I plug in n divided by 2 for this, then I get n divided by 4. Right? So 2 c sub n divided by 4 plus n divided by 2 minus 1. Right? And then don't lose the original either. Plus n minus 1. There's the original. Right? And you do it again and over and over and over again until you get down to the base case, basically, where you've got an array of size 1. C sub 1 is 0. You don't make any comparisons. Right? What's one more iteration of this unrolling? 2 times 2 times 2 of c sub n divided by 8, right? Plus n divided by 4 minus 1 plus, don't lose the original, n divided by 2 minus 1 plus, that's well balanced, n minus 1, right? You keep doing that and you start to see a pattern. 2, 2, 2, that's going to be 2 to the third. What is 8? 2 to the third. 1, 2, 3 iterations of the recursion. Dot, 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 you get down and you solve it. Don't do that. All right? That's a lot of math for not a lot of payoff. Instead, bring what's called the master theorem to bear. Yeah, there we go. The master theorem, it's really not a master of anything. It's it's actually quite limited in how you can use it. It says if you have a recurrence of this form, where you're making a certain number of recursive calls, right? A is the number of recursive calls, right? B is the factor you cut the input by. Right? So for our case, right, we were cutting it in half each time. B would be 2. And then f of n is the non-recursive cost. Okay? That's some function. If you can bound that function by a polynomial, n to the d, then you've got a, b, and d. Using those 3 things, you plug and chug. This first case here is when you are making fewer recursive calls than you are doing non-recursive work. The third case here is when you are doing more recursive calls than you're doing non-recursive work. And this third case is when you're doing roughly an equal number of recursive calls and non-recursive work. In any case, it doesn't matter, right? Again, it's just a tool that you use to plug and chug. For quicksort, we have that C sub n is equal to 2C sub n divided by 2. 2 recursive calls, cutting the input in half each time, and making a linear number of comparisons. So here A is 2, B is 2. What is D? This function right here, f of n, give me an asymptotic characterization of it. It's order what? Certainly it's at order n squared, right? That's true, right? But that's not as helpful. What's more true? N. Right? It's just a linear function. And so consequently D is what? What is the exponent that's hanging implicitly up here? 1. So A versus B to the D. 2 is what of 2 to the first? They are equal. That gives me case 2 of the master theorem, which was what again? This thing right here. T sub n is going to be order n to the d log n. What was my d again? Order n to the first, 1 log n. Do you remember what selection, sort, and quicksort were? N squared? Is this better? Oh yeah, this is way better. Right? Again, this is going to be the difference between, literally, it's going to be the difference between 20 plus years and 2 minutes to sort something, right? Because this is we call this quasi-linear, right? Almost linear, because it is linear except for this logarithmic factor out here. You'd have to get, you'd have to get extremely large for this logarithmic factor here to even matter at all. And there aren't enough computers in the world in all of human history to reach that point, right? Logarithms grow so slowly that it doesn't really matter. Right? You could sort all the atoms in the known universe, right? And this log factor would be less than 100. So who cares? Right? In fact, we have an expression for that. N log n is equal to big O with this tilde above it of n. It's quasi-linear. When you ignore the lower order, when you ignore multiplicative log factors, you can go ahead and just throw them out the window because it doesn't matter for all intents and purposes. Okay? Well, we've got 35% left. So what can we do with 35%? Let's see. We can do another example, or we can go back to binary search. Binary search. In fact, again, since we're at 35%, is that it? Let's go over here. Binary search, recursive. There we go. There's a recursive version of binary search. Let's analyze it with respect to the tools that we just developed. The same trick. I'm going to go ahead and establish that C sub n is the number of comparisons performed by binary search on an array of size n. Okay? Now, what's the recursive cost here? We make a recursive call here and a recursive call here. Do we actually make both of these recursive calls? No, why? If, else. They are mutually exclusive. At most, we're going to make one of these recursive calls, right? So, oops, get rid of that. One recursive call to binary search on how big of an input now? How does binary search work again? It halves it each time, right? That's why we call it binary, right? N divided by 2. Okay. How much non-recursive work are we doing here? How many non-recursive comparisons are we making? 1, 2. Okay, if you wanted to do it that way, we could. We'll go ahead and say 2. Really, is that 2 though? That's probably going to be, in practice, that's going to be a call to a comparator function that gives you something negative, positive, or 0 depending on the relative ordering of things. That's my elementary operation, the call to that comparator function. Once I've got that negative, positive, or 0, now that actual integer comparison is necessary for the control structure of the algorithm. Who cares? It doesn't really matter. We're going to come up with the same analysis. 2, 1, it doesn't matter. Why? Because of the master theorem. What is my A in this case? 1 recursive call. What is my B? Let's bring up the master theorem again. Nope. Where are you? There we go. What is my B? 2. And what is my D? Well, it's this function right here. This is order what? It's certainly order n, right? That's just as true. But what's more true? A constant is going to be order 1. You can write it like that. It's just a constant. If I were to write that as a polynomial, though, what would it be? N to the 0. Good. D is going to be 0. So A versus B to the D. A is 1 versus 2 to the 0. Guess what? They're equal again. And by case 2 of the master theorem, I have that binary search is going to be order n to the d log n. Well, what was d again? 0. It disappears. So binary search, its complexity, C sub n, is going to be order, remember that n to the 0 goes away, and we're left with log n. The exact same complexity that we came up with when we did it in an iterative version, and we just simply summed everything up. Right? But now we're using the master theorem as this tool, and we don't have to solve anything. No math involved, other than setting up your recurrence, identifying A, B, and D, and then plug and chug. Right? Okay. Let's see. Good on that. Yeah, go ahead.
Because it's big O log, is it basically the basic equal to a constant?
If you use that tilde. Yep. Because, I mean, think about it this way, right? How many comparisons would you need to make in binary search for, I don't know, log base 2 of 10 to the, how big is a trillion? 10 to the 9? Is that right? No, that would be, yeah. 1 million would be 10 to the 6th. Billion, 9, so trillion is 12. There we go. Less than 40 comparisons, right, for a trillion things. How many to search every single atom in the, every single atom in the known universe is now sorted in one big line. And you were searching for a particular atom, right? You would only need to make 332 comparisons for every single atom in the known universe, right? Anything that you can put into a database will never, ever require more than 300 comparisons if you're using linear search. Or if you're using binary search, right? If you're using linear search, yeah, you're screwed, right? Right. In fact, I think I've got a screenshot, an old Windows screenshot in the book that I'd like to share. Where is it? Find Windows. No? All right. I don't know where it is. Darn it. Sorry. There's a list of figures somewhere. No? Come on, really? Where's linear search? Anyway, Macs, no, a Mac right there, Windows. So on a Mac, you sometimes see those DS store files, right? On Windows, I'm sure that you've got something else that's hidden, like DS store, right? Right? On Windows, I don't know what it would be, but find index. Oh, come on. Oh, wait, no. Found it. No, I didn't dig it. Where are you? It's a screenshot that I took on the last time I had a Windows machine. I'm about to give up if I can't find it. Has anybody used the Computer Science 2 textbook at all? The free one that I've been posting?
Is it textbook?
Well, I wrote it. That's why it's free. Well, wait, I wrote it with an index. Binary search, where are you? Binary search. Nah, darn it. Okay. It was somewhere in here. Anyway, what's the point of that DS store file? Does anybody know? It's to index things. It's to come look at all the files and all the contents of your files in the system, and then it builds a sorted list of all of them. Right? Why does it build a sorted list? If you're searching for something, which one's going to be faster? Searching a sorted list for keywords, a sorted data structure for keywords, or having to go through every single file over and over and over again. Right? One of those is binary search. One of those is linear search. And one of those is going to be orders of magnitude faster than the other. Right? You're talking about 300 comparisons instead of 10 to the 100 comparisons. Right? Something that is completely infeasible by any computer at all in the known universe versus something that can be done on any old desktop. Right? As long as you have it sorted first. And that's what computers do. You like to go through and you like to sort things because you like fast retrieval. Google does not, every search that you make on a Google doesn't go out to every single website when you ask for it, right? It has crawlers that go out and index things and then put them into data structures that are sorted so that you can have this order login, essentially constant time behavior. Right? And the screenshot that I had at some point was a Windows screenshot telling us that searches on unindexed files will be slow, or something like that. I forget what it was. I swear I had it. Maybe it's in the other book. Maybe it's in the Computer Science 1 textbook. Did anybody use the Computer Science 1 textbook? Okay, there. Yesterday when you needed the algorithm. All right, I'm not going to be able to find it. I don't know where it is. I might have a screenshot of it in my CS1 files, though. Are you there? Nope, I don't have it. Oh well. I give up. All right, so algorithm analysis. Any questions? No? We still have 20%. We could do more examples. If you want to give me two functions. What about, well, here, let's just set up a relative ordering of functions, right? What if I had, I think we've done this before maybe, but the least complex ones are going to be constant time, right? What about order, let's say, order n squared versus order n? Where should I put order n? Above or below? Right? If this is going to be lowest to highest. And we mean by order of growth. Right? So now where should I put a linear function? above. Right? Give me some other functions. Log n, the one that we just did for binary search. Binary search. What would be an example of an algorithm that would not take any time at all? Well, it would take a constant amount of time. Maybe a formula computation, right? 2 times n. That's actually super easy, right? And you shift it over by 1. You multiply it by 2. Right? All right. Give me an example of a linear algorithm that we've seen. Oops. Linear search, exactly. Right. Linear search. Give me an example of a cubic. Insertion sort. Selection sort. The painter that doesn't pick up the paint bucket, right, etc. Give me something in between here. And log n belongs in the middle. Quicksort. And if you saw it yesterday, merge sort. Or the built-in sorting algorithm in routine, I should say, method in Java uses Tim sort. Yeah, Tim's the guy that wrote it. He originally wrote it for Python. It's basically a modified bottom-up merge sort that doesn't use top-down recursion. It builds up sequences of sorted things and then merges them together. Right? Well, order n cubed. If you want to, you can be general about it, and this is just polynomial. Right? This is logarithmic, linear, quasi-linear, quadratic, cubic, polynomial. What's above that? Oh, okay. Let's go ahead and go with just constant 2 to the n, right? And then you say order n to the n. Wow, that's super. That's exponential and super exponential. Right. Examples of that, say from 235, order 2 to the n will be computing all subsets or combinations. Right? For example, if I had A, B, C, how many possible combinations are there of A, B, C as a set? Well, there are the singletons, A, B, and C. There's the empty set. There's the set of all elements, A, B, C. There's the set of doubletons, which would be A, B, A, C, and B, C, right? That's going to be exponential. There are 3 elements here. It's 2 to the 3rd. Okay? You guys do this in 235, right? Okay. What's an example of a super exponential? Say, n factorial. Computing, not combinations, but what's their cousin? Ordered arrangements of permutations. Again, A, B, C. 3 here. 3 factorial is what? 6. So how many arrangements are there of ABC? 6. ABC, ACB, BCA, BAC. That one should actually go first there. Right. What else? CAB, CBC, CBA. There we go. Right. So, is it, for example, feasible to figure out how many how many pairs you have, how many pairs of poker hands that you have by looking at all possible shuffles of a 52 card deck? 52 factorial. Yeah, that's big. That's way too big. In fact, when I do combinatorics and say 235 or something, I ask, if you were to shuffle, if every 5 billion people were to shuffle a 52 card deck 1 second of every day for the entirety of human history, you would have only explored 0.0000020 zeros 1% of all possible permutations of a 52 card deck. Right? No, it's not at all feasible. In fact, what's not feasible that we already know from the experiments that began all this? Anything above that, right? For large inputs. N squared, N cubed, okay, fine. You're going to be sitting there for a while. You might want to look for a better heuristic. But certainly anything over, say, what did we start out with? Like 1 billion? Because that's going to take 20 years. Small input sizes, yeah, sure. Go ahead and generate every single possible subset of ABC. Right? It's not going to be all that useful. But once you get up, say, to 10, 20, 30, nope, you're pushing it. It's not gonna execute. You need to look for a different solution. All right? We made it with 8%. See you next weekend, or see you next week. Have a good weekend.